Turing machine. In other words, we've accepted the fact that Turing machines are algorithms, but we've also shown that Turing machines are limited. There are problems that exist that are not computable. Therefore, in a sense, algorithms are also limited. But that's the big picture. I don't want to call it a small picture because, of course, it is still a big picture. But I want to change our focus here to problems that are computable. That is, problems that do have a Turing machine. Every problem that you've looked up, that you've had up to this point, Hamiltonian path, Hamiltonian cycle, given a graph is S connected to T, sort these things, sum these things up, find the average, find the mean. All those things are computable problems because you've written algorithms for them. You've designed a Turing machine, if you want to look at it that way, for those problems. So what I want to ask instead is, within the problems that are computable, do some problems require more resources to solve, right? Are some problems inherently more difficult than others? Can we start to say that this problem is just as hard as this problem, or this problem is provably more difficult than this problem over here? And more difficult means more resources are required to solve it. Now, up to this point, you have been analyzing algorithms, right? Big O notation. This analyzes algorithms, right? Given an algorithm, algo, how good is it? Right? If you can say, well, it's linear, then it's pretty good. If it's n squared, not very good, but it's still okay. It's exponential. Okay, no, that's out, right? That's an analysis of algorithms. What I want to do is I want to change our focus. Note that what I underlined here. Among problems that are computable, are some of them more difficult than others? So our focus with what's called structural complexity is not to study algorithms. Algorithms are part of it, but studying algorithms only establishes an upper bound, right? If you can come up with an algorithm that operates in order n log n to sort things, then that's a good algorithm. What I want to do, that establishes an upper bound, that there is an algorithm to do this and it operates in this time. The question I want to ask now is that the best you can do? In other words, I want to establish basically a lower bound. This is the minimum number of resources required to solve this problem. Okay? So structural complexity involves establishing, studying problems, not algorithms. Algorithms are solutions, right? And that's what you've been doing over the last year, CS1, CS2, and discrete math. Given an algorithm, use big O notation analysis to tell me how good it is, right? Now what we're going to do is we're going to say, given this problem, not this algorithm, given this problem, what is its inherent difficulty, okay? So to do that, we need a notion of resources with respect to Turing machines, okay? Now with big O analysis, you say, well, what's the input? And what's the input size, right? And so the equivalent to these is the input is always going to be a string with respect to Turing machines, right? Remember, this is the set of all strings. X is simply a binary string that's in this set. Our input size is going to be, input size will be the size of X. Now, this is used in other, this is a norm, or this is the absolute value, or something like that. This is just going to be the length of X. So it's the number of bits in X when it's written on the input tape of a Turing machine, okay? So that's going to be our input size, right? Now, with respect to the other steps, that's 1 and 2. What's 3 is that we need to identify an elementary operation with respect to a Turing machine, right? 3. What's the elementary operation? Well, the elementary operation is just a state change. Remember, a Turing machine has an input tape. It has this output tape. And then it has this finite state control that is pointing to an input and pointing to an output. And based on what it sees in the input, based on what it sees in the output, it makes a state change within this finite state control here. So it's simply just a state change, going from one state to another state. Another state. Now, from the perspective, that's kind of capturing time, right? Because if you can say that you can do 100 state changes per minute, right? Well, then that corresponds to time, right? And if it's an actual computer processor that can do millions of state changes per second, or billions of floating point operations per second, then that's basically the same thing. How long does it take for your processor to go from one state to another state, i.e. time, right? So when we say that a Turing machine operates in T sub n, another way of writing that is simply just the length of n, then this is the number of state changes made, I don't want to say required, but made by a Turing machine on input sizes, inputs of size n. Right? And that's going to be our notion of time. Right? So you can look at this as time taken by an algorithm or Turing machine. Right? So everything that we've discussed over the last year, big O notation, it has some analog and some interpretation with respect to Turing machines. We won't go over it, but of course you can also define memory, right? How would you define memory with respect to a Turing machine? Remember, the input is read-only, so you can't use it, you can't abuse it, you can't leverage it. You can read it all you want, go back and forth, read it a million times. But your real memory is that output tape, right? So you could interpret the memory used by a Turing machine as the number of unique, if you want to, because you can reuse cells down here. You can overwrite them like we did with our Turing machine algorithm that decided that language 0 to the n, 1 to the n, right? All we did was write a bunch of zeros and then we erased them. We overwrote them. It's the number of unique memory cells, that is bits, used in the output tape. Okay? So if you can bind, so again, we're going to focus on time here instead. Of course, if you wanted to focus on memory, that gives you an entire different landscape for all of your complexity classes. Our first complexity class, though, based on time, is going to be P, right? And we'll say that let let M be a Turing machine such that the time that it takes to operate on inputs of size n is going to be bounded by some polynomial, right? Then we say that this is for all n, right? Then M is a polynomial, let me write it out fully, deterministic polynomial time, right? Polynomial because the time is bounded by some polynomial, or P time, Turing machine. This holds for all n, okay? If it's bounded by some polynomial here, okay? Now that gives us a notion of polynomial time as a complexity class. P. This is going to be all languages L, such that L is a language, such that there exists a polynomial time, P time, deterministic Turing machine that decides L. Now remember the definition of decision. That is, for every input, it has to halt and stop and say, yes, it's in the language, or no, it's not in the language. If for any input it goes off and it goes into an infinite loop, then we don't say that that Turing machine decides that language. Most of the algorithms that you've designed up to this point, especially in CS1 and CS2, they are polynomial time algorithms. Therefore, if you want to translate the problem that you are solving into a language, that language is in the complexity class P. Some things to note about this. P is a class of languages, not machines, by definition. L is a language such that there exists some machine that decides it. It's a class of languages, i.e. problems. All right? We can say that it's the class of problems that have efficient solutions. This is, and I put efficient into quotation marks here because it's efficient with respect to a theoretical point of view. As you've all seen, is order n squared efficient on big data? Absolutely not. Right? There are, as you saw in your first homework, if you tried a brute force solution that was, it's still polynomial, order n squared, but if you did that, you'd be sitting there for weeks because of the nature of the big data. Right? So, but we're still okay for that. In fact, we're okay with order n to the 100 algorithms. Right? That still follows into this class of problems here, that there is a polynomial time solution. Now, there aren't many natural problems where you only have this as an algorithm and that's the best you can do. It's kind of unnatural. The vast majority of algorithms that are of real concern are going to fall into those categories of polynomial of linear time, quasi-linear time, order n squared or order n cubed, right? There are not many problems that lend themselves to 100 nested for loops, right? But from a theoretical point of view, this is still the class of efficient solutions. Right? So give me some examples of things that are in P, languages or problems that are in P. Right? What are some problems that you've solved with a polynomial time solution? What's one application of, say, DFS? What can you do with graphs? What kind of questions can you ask about graphs? Does there exist a cycle? Right? Is a graph G acyclic? You can use DFS. DFS operates in linear time. What's something that you did in CS1? Searching and sorting. Those are easily solved problems. Given a collection, output its ordering according to some ordering. Right? Output a sorted collection according to some ordering. Right? Computing, say, matrix inverse, or solving a linear system. That's one you did. Right? Just think of all the algorithms that you've written up to this point, all the programs that you've written up to this point. Here's another one, though. Question. What about one that you have written, but it was kind of exponential? Hamiltonian path? Is that in P? I don't know. The algorithm that I showed you certainly was not in P. It was not a polynomial time algorithm because it enumerated every single possibility. Right? What about satisfiability? Given a Boolean formula, does there exist an assignment such that it evaluates to true? Right? Remember that there were order 2 to the n with that algorithm. Up here there were order n factorial for that algorithm. Right? Those certainly are not polynomial time solutions. But that doesn't mean that there's not some polynomial time solution out there. To answer that question, we have to establish, well, I mean, these seem to be easy. This seems to be hard because the only way that we know how to do it is brute force and exponential. Is there a connection between these two things? And that's what we're going to answer today with the introduction of complexity classes. But before we get there, we need a brand new notion of magic computation called non-determinism. All right? Now, you'll remember in the definitions that I gave over here, I added this word deterministic. What does deterministic mean to you? Kind of sounds like determined, right? That you're determined to do something, you're set on it, right? Well, in this context, determinism simply means that there's only ever one outcome. That if I have this input, and I run this algorithm on this input, it'll produce the same computation every single time. It's not randomized. It doesn't make random guesses. It doesn't, it doesn't change. It's determined, right? How it's going to actually compute, because it's written down as pseudocode, and for the same input, you'll have the exact same computation. If you have a sorting algorithm like selection sort, and you've got 5 elements, and on the first run of the algorithm, it swaps these 2 elements. Every single run of the algorithm, if you rerun it and run it again, it will always do it the same way. That's what determinism means. Its computation is determined. Right? Non-determinism is completely different. It's a magic computation. And by magic, I simply mean that it's theoretical, right? It's a theoretical idea of computation. It doesn't actually exist. Does not really exist. But it turns out that it's so useful from a theoretical point of view to talk about non-determinism because it closely matches a whole bunch of problems that it's really nice, right? It can always be simulated by deterministic computation, but with an exponential blow up. That is, if I gave you exponential time, you could actually simulate this non-determinism. Right? It's a way of capturing kind of exponential amount time and fitting it into polynomial time. Okay. So it doesn't really exist. And 2 other comments I would make is it's not randomization. Right? You might have seen some randomized algorithms that that randomly select inputs and then try things, or randomly try to generate things, or use random bits or something like that. That's not the same thing as non-determinism. It's not. Another thing that you might have heard of is quantum. Right? Quantum computing. Quantum computing is fundamentally randomization, but it's guided randomization. It exploits quantum operations to basically force the quantum system to an actual solution, but it's still going to be randomized. There's still a probability that you won't get an answer when you measure all your qubits, right? So these are other models of computation. They're real. They're kind of real, but not on a big scale yet. So they're not the same thing as non-determinism. Non-determinism is fundamentally magic, right? It doesn't really exist. It's a theoretical model of computation. So how does it work? There are 2 stages to a non-deterministic algorithm. Stage 1 is the guess phase. A solution is guessed. So it is generated, but it's not generated randomly. Okay, there is no randomization here. You guess a solution. and you call this called a certificate. All right? This certificate either gives you a realization that yes, it's in the language, or no, it's not in the language. So what we have to do is we have to go with a second phase of verification. All right? If I gave you a certificate, where have you heard certificate before in the context of computer science? Think security. No? Go to Amazon.com and look at your browser, and it gives a little, depending on your browser, there's a little green OK symbol up at the top, right? Because it's HTTPS. There's a certificate granted by, or that's generated by a certificate authority that says this person is who they say they are, right? And you don't just take it as face value. You take this certificate and then go on to a certificate authority and say, this person has this certificate and says that they're Amazon.com. Are they correct? And they say, no, that's a fake certificate, or it's an expired certificate, or yeah, that's a valid certificate, that's Amazon.com. Right? It prevents man-in-the-middle attacks so that you don't go to Amazon.com and get caught with your credit card, and they steal your credit card information or whatever, right? So the verification phase is that you verify the certificate. And if valid, you accept. Remember, we're talking about Turing machines here. Turing machines have two universal states. They have an initial state, all their finite state control, and then at the end when they halt, they either halt and accept, that's an instance of the language, or they halt and reject, that's not an instance of the language. Right? There is a Hamiltonian path, there's not a Hamiltonian path. Right? So if valid, you accept. If invalid, you reject. Right? And if any guess leads to an accept state, then the Turing machine, or the algorithm, which we're going to talk about in terms of algorithms here, accepts. Okay? So let's look at a couple of examples. First of all, we'll look at a concrete example, and then we'll look at a visualization of an example of the two problems that I just mentioned. So here's a non-deterministic. It's not hyphenated, by the way. It's non-determinism, one word, so yeah. Non-deterministic algorithm for Hamiltonian path. Okay? So I label my input a graph, G equals V, comma E. And step one, guess a path, P, which is a permutation of vertices of V. Right? So we'll call it permutation of V. Okay? Equals V1, V2, dot, 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 Vn. That's going to be our certificate. And now we need to verify the certificate. So for I, running from 1 up to n minus 1, if V sub I plus 1, is not an edge, then this is an invalid certificate, because this is not a valid Hamiltonian path. Right? So we reject. Right? Otherwise, if you go through every single possibility, and this is an edge, and this is an edge, and this is an edge, then we output, or we don't output anything. We're a Turing machine, remember? We accept. Right? And that's it. Right? Now, I'm abusing pseudocode to the absolute max here. How did you guess it? Well, you could say, well, I randomly permuted all of the vertices. That's not non-determinism. Using randomization is not non-determinism. How did you do this? It was magic, Right? It's a theoretical construct that you can't actually program. Right? There's no such thing as non-deterministic version of Python. There's no such thing as a non-deterministic version of Java. There's no programming language that will allow you to do this. There's certainly not a machine that gives you non-determinism that can be built in the real world. And there's certainly not a Turing machine that you can actually build out of this. It's a theoretical point of view. Okay? And we'll see why it's useful here in a second. But otherwise, this is deterministic. This is a deterministic verification. Right? This is the non-deterministic guessing phase. Right? This is the magic phase. There's no magic here at all. Right? You're just verifying that that's a Hamiltonian path or not, and then you reject it. Okay? Here's another way of viewing it. And here's the visualization view. Remember the satisfiability problem, that if I gave you a Boolean predicate on n variables, the way that we ended up doing this with pseudocode was we took the first variable and we said, okay, well, it can either be 0 or 1. The second variable can either be 0 or 1. 0 or 1. The third variable, x3, x3, x3. I want 0 and 1 on my edges, right? And I won't draw the entire tree, but way down here at the bottom, right, this is a magic computation path. This leads to some x variable, right? Well, here's another computation path. And that leads to some other x variable. Right? In fact, all of these lead to some assignment. How many of them are there? 2 to the n. Right? Now, a non-deterministic Turing machine would guess one of these assignments and either accept or maybe reject. But the entire machine does this basically, and it's not parallelism either, but that's another way of thinking about it. It does all of these things at once magically, okay? And then if any one of it accepts, if any computation path accepts, right? So for example, if this were a satisfying assignment, it would accept, and therefore the entire machine would accept. If all of them rejected, then it would not be satisfiable and the machine would reject. It gets to do this stuff by cheating. It doesn't have to generate every single exponential assignment. All it has to do is guess. And now, how much does it have to guess? How many bits does it have to guess? Well, 1 bit for the first one, 1 bit for the second one, 1 bit for the third one. What's the depth here? Order n, right? So non-determinism allows you to do an exponential amount of things by only keeping a viewpoint that it's polynomial, right? Again, that's why it's magic. And that's why I said that you can simulate non-determinism, because that we did that very thing with brute force algorithms. All you need to do is generate this entire tree. And if you generated this entire tree, of course, you could go over each and every single one of these, and if any one of them accepts, stop, prune out the rest, you're done, answer yes. But in the worst case, when all of them reject, you would end up having to generate all 2 to the n possible computation paths here, if you were to do it deterministically. Okay? So it's kind of trippy, but it turns out to be very useful. Why? Because it gives us the power of first order logic. Right? Another way that you can look at satisfiability is by looking and asking a question about an existential quantifier. Does there exist an x1, an x2, an x3, ... xn, such that this predicate on x evaluates to true? Right? Very compact way of representing this thing. It's basically asking, does there exist a truth assignment at the bottom of this computation path that accepts? Right? That, in other words, that it evaluates to true. Right? But you're basically granting it the power of an existential quantifier here. Right? And you can talk about universal quantification. That's non-determinism. It's a different. You just flip the criteria. If they all reject, then you accept. If any one of them accepts, then you reject. So it's just the opposite, right? And that gives you a universal quantifier right here. Right? This is exactly SAT, right? And it was so motivating that it gave rise to this notion. How do we capture the idea of this logic? We capture that idea with this idea, with non-determinism. You can magically get the power of this quantifier here by only looking at a polynomial number of things in your certificate, right? So it's like giving you the power of this existential quantifier as for free, basically, right, in your computation. Okay. All right. So that's non-determinism, and it allows us to define a non-deterministic polynomial time, NP, equals non-deterministic polynomial time. And it's simply all languages L, such that L is a language, such that there is a non-deterministic polynomial time Turing machine that decides L. Okay? That's the exact same definition as P, except the only difference is that instead of deterministic polynomial time, it's non-deterministic polynomial time. In other words, all of the problems such that if I gave you the power of an existential quantifier, or if I gave you this extra power called non-determinism in order to do an exponential number of things all at once, then you could you solve more problems, right? And as we've seen, yes, Hamiltonian path and satisfiability, they have NP solutions, right? So do they have P solutions? Are they in polynomial time? That's the big question. P versus NP. Right? Is this inherently more powerful? Right? You can always simulate this with an exponential blowup, but is non-determinism, can it be simulated by only a polynomial blowup? That's a big question. Right? Clearly we know the following. P is a subset of NP. Why is that? Let me get the definitions again. Where's my definition of P? Here we go. There's my definition of P. There's my definition of NP. Why is this inclusion? Any polynomial time problem is also a non-deterministic polynomial time algorithm. Why is that? Because you can always skip the magic guessing phase and compute a solution, in other words, a certificate, directly. So this is basically by definition. Right? All you're doing is ignoring this extra power that I'm giving you. Right? If I gave you $1,000 to do a task and you did it with only $100, and I knew that it was only going to take $100, then this $900 that I gave you, you ignored it, you didn't use it. Well, that's okay, right? If you don't use that extra powerful that extra power in your computation, then you don't have to, right? But so that's what's known, right? The other question is NP a subset of P, or is, in other words, if you establish both of these things, is P equal to NP, or IE here, or is P not equal to NP? Right? The answer, if you take this answer, then this means that non-determinism is not inherently more powerful. Something that seems like it has a lot more power, if you were to actually prove this, then you'd be saying, no, that's not actually the case. It's not inherently more powerful. In other words, you could simulate this magic non-determinism with an order n to the k algorithm determinism, right? And that would be huge. If you said this means that non-determinism is inherently more powerful. And this establishes a relationship that says that some problems are inherently more difficult, i.e., some problems are inherently more difficult. Now, with respect to P and NP, still nobody knows. This goes back to the early 70s, so we're talking about 50 years old now, and still nobody solved this problem. In fact, it's one of the Millennium Prizes. That 19 years ago, they established 7 Millennial Prizes. I think it was the Clay Mathematics Institute. There were 7 mathematical problems that were still open, and they offered $1 million for it. $1 million is just, marketing, basically. It's just a gimmick to try to get people interested in these things. One of them was solved already. Did you hear about the Poincare Conjecture? Some Russian mathematician solved it, refused the $1 million, refused the Fields Medal for whatever reason, just because he's weird. He wants to keep to himself. But he solved one of these problems, and there's $1 million sitting in the bank for him that he's never going to claim. So I don't know what's going on with that money, but this is one of the other problems. There are several other problems, like I think the Zeta function, the Riemann Zeta function is one of them, and a couple of others. But this is one of the big ones, and for computer science, this is the biggest is one of the biggest questions. Okay, are there things that are inherently more difficult? Are there problems that are more difficult than other problems? Now, with respect to other there are actually hundreds of complexity classes. And there have been questions answered that problems in this complexity class are inherently more, I want to draw it like this, problems in this complexity class are inherently more difficult than this complexity class down here. Unfortunately, they are either really easy to show this because of their by definition, or the separation is so far apart that it doesn't really matter. For example, parity. Parity is in a complexity class called AC0, and that has been separated from, say, P or whatever, right? It's a very, very low class that's been separated from a much larger class. So some questions have been answered in that regard, but these bigger questions have not, right? In fact, the progress in this direction has been very slow. Only about every 10 years does somebody make a little bit of a dent in this kind of progress. Of course, you'll see proofs purporting to show this or this, and usually by crackpots, saying that really don't explain their proofs. They don't have much of a proof. They refuse to submit it to real journals. They'll just throw it out there on the internet or archive or whatever and claim to have solved this, wanting the $1 million, but of course, the bots. The question is still open, okay? So, how do we don't know the relationship between P and NP, right? The final relationship. But are there relationships that we can establish between those problems? Okay. And that's what we're going to talk about for the rest of the day. In fact, the rest of the class, reductions. All right? So reductions are a way of establishing a relative complexity between problems. All right? And we're not going to be able to say that this problem is definitely more difficult than this problem over here, but we can establish relations that of the following form. We can say that a problem B is at least as difficult as a problem A. Right? That's establishing a reduction. And the way that we generally write this is A reduces to B. I'll define this more generally here. We read this as A reduces to B. This is not reduction as in simplification. All right? Reduction. Reduction is in like you're taking things away, right? You're taking your divide and conquer approach. That's kind of a reduction in that you're reducing the problem size into something that's half as large, and theoretically it's easier to solve, right? It's not that kind of a reduction directly. What I do like to give an analog to is cooking. Does anybody cook for themselves? Right, what's a reduction? Nobody cooks for themselves? No? You've gone to a restaurant before, right? Maybe not. Maybe you've never gone to a fancy restaurant where they've got like a roux. Have you ever heard of a roux? Like a sauce? Right? You do a reduction. What's a reduction? You boil it away, right? You boil away the unnecessary stuff. You boil away the excess water, and you reduce it down to its essentials, right? It's not a simplification. It's a reduction to the essentials. That's what I like to think of it as, right? But admittedly, this is a horrible term, and I think that if they had to do it over again, they could come up with something much better. Right? Have you ever heard of the lamentation that there are only two things that are difficult in computer science? One is cache invalidation, and the second one is naming things, right? So computer science has a terrible reputation for naming things. Non-determinism, determinism, right? That's just whoever came up with the idea first, they needed a word, so okay, I'll pull that word out of the air, and because it kind of has a tenuous grasp to this, they also pulled the term reduction out of the air, right? This is what I like to think of it as, though, right? This establishes a relationship. B is at least as hard or complex as A, right? And note that it's less than or equal to. It is not necessarily more difficult. If we could establish that, we would have instead used a symbol that looks like this, right? Strictly less than. And we don't use that because we can't establish those relationships yet because we don't know what the relationship between P and NP is. Right? All we know is that I can take one problem and reduce it to another problem. Okay? Now, before we look at the formal definitions of this, you've done this before, right? I'm going to call these Turing reductions because that's what they are, without giving you the formal definition. But consider the following. Maybe we've got a pseudocode language here. Here's a Boolean. Here, I've got a library of functions. Bool is connected. It takes a graph and two vertices x and y. Right? I think we've looked at this kind of before. And then I've got another function called int. Right? It's shortest path distance. And it takes the exact same input, g, x, and y. Right? And then I've got, say, a list of vertices. So I'll go with Java-like parameterization right there for that one. Shortest path, G, X, Y. All of them take the exact same input. This one, however, returns a Boolean. Yes, in G, X is connected to Y. Right? This one answers a slightly different but related question. Between X and Y, what is the shortest path, the distance of the shortest path? This one answers yet another question, but different question, but related. The shortest path, I don't care how long it is. I want to know what it actually is. Between X and Y, give me a list of vertices, X, A, B, dot, 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 up to Y. Give me that list so I can actually go on that shortest path. Okay? Now here's a reduction. I wrote these as algorithms, but think instead of these as problems that I have to solve. Given a graph, given two vertices, you have to actually implement this function. You have to actually implement this function. You have to actually implement this function. Which one of these things would be the easiest to implement? The what? The Boolean one, right? Because just finding out whether or not a path exists, that seems like it's a little bit less information than finding the shortest path. Right? What about shortest path versus shortest path distance versus actually getting the shortest path? Is there a relative, an intuitive relative complexity there? Which one of these is more difficult, do you think? Or at least as difficult, I should say. Finding the shortest path, right? Why? I'll leave that one as an exercise for you to think about. Let's establish that this is actually easier than this, okay? Let me go ahead and implement it. Is connected of G and X and Y. So this is kind of looks like Python or something, right? Let's suppose that somebody else came along and did this one for us. Let's suppose that somebody already implemented this for us, right? I'm going to call that, right? This goes back to the DRY principle in CS1. Don't repeat yourself. If you can implement this algorithm using another algorithm, do it. Don't reinvent the wheel. So what I'll do is I'll create an integer here. I'll call it length is equal to shortest path distance of x, or g, x, and y. And it returns an integer, right? We could also say that it returns, infinite if no such path. Otherwise, it returns an integer k, right, representing the length of the path. Now, the question I want to ask is it connected? All I need to do is ask if shortest path, or length, sorry, I stored it off in length, is finite, then return true. It is connected because there's a finite path between them according to this other solution over here. Else, return false. Now, why does that show that there is a relative complexity here? Right? So, suppose that I have a reduction from A to B. Right? 2. Suppose you have an algorithm for B. Right? Does that give you an algorithm for A? 3. You can build an algorithm for A. Right? Use A, run the solution for B, and use the solution to answer A. Right? And that's my algorithm for A. Right? I just basically made this thing super abstract. What is A in this case? Is connected is A. B in this case is the second one. And I said, suppose that somebody already wrote this for us and put it into a library. Suppose that there was already a solution for this problem. How do I design a solution for the first problem, A? Well, I simply use the solution for B and then answer a question about A instead. This establishes that is connected is no harder than shortest path distance. All right? Now, it doesn't say that this one is inherently more difficult. We could establish the inverse relationship as well and say that they are computationally equivalent because you can use one to solve the other and this one to solve the first one. Right? You can do that, by the way. Right? But the interpretation here is that is connected is no harder than shortest path distance, SPD. Hopefully that doesn't stand for anything bad. I don't think so. All right. And shortest path distance, SPD, is at least as hard as is connected, or con for short. Right? These are kind of weasel words here. Is at least as hard, is no harder than. That's because we've got this less than or equal here. We can't establish that one is inherently more difficult than the other. And that's the idea of a reduction. Okay? Here's a formal definition of what are called mapping reductions. I like to, before we look at that, again, I like to look at Turing reductions because it's something that you understand already. Anybody that knows programming, anybody that has gone through a CS1, CS2 course, and has picked up the best practices of the DRY principle, don't repeat yourself principle. Anybody who's designed functions, and so that this function can use this function over here. What you've been doing this entire time is theoretical. It has a theoretical component called reductions. Right? That's a great way of looking at it, and that's why I like to present that one first. But theoreticians wanting a more rigorous definition will always come up with a more difficult way of putting something. So definition. Let A and B be problems. Right? A, polynomial time reduces to B. And by the way, for anybody that sees these videos on the internet or whatever and can criticize me, can definitely criticize me here for using the wrong notation. This is a polynomial time reduction. I was talking about Turing reductions. That has a different subscript of T for Turing reduction, right? But it's okay. This is not a complexity class. This is just a CS3 class. This is a polynomial time reduction, okay? In other words, A is poly time reducible to B if there is a poly time computable function F such that F maps strings to strings if X is an instance of the language A, if and only if F of X is an instance of the language B. Right? In other words, yes instances of problem A map to yes instances of problem B. Right? And likewise, no map to no. Okay? And of course, I wrote it up here, but I'll emphasize it down here. f is deterministic, computable by a polynomial time deterministic Turing machine. Okay? All right. Now, we'll look at this by looking at several examples. But what I want to do is I want to look at the idea that these establish relative complexities. Okay? So this function here, how can we use it to solve problems, basically? So suppose you have an algorithm. What do I want to call it here? B for problem B. I'll abuse it and call it problem and an algorithm at the same time for B, right? And also further suppose that A reduces to B in polynomial time, right, via a function f. Okay? Now what I'm going to do is I'm going to design an algorithm, A for problem A. Again, I'm going to abuse these things and I'll treat them as synonymous. Okay? Here is my algorithm that gets an input x. It's this box. Okay? The input to this box is x, which is simply just a string. Okay? What we're going to do is we're going to feed it through f here, f of x, right? Which outputs another string y. Right? Then we're going to feed that output string into our supposed algorithm B for problem B. And it's going to output one of two things. It's going to output yes, or it's going to output no. That y is an instance of the language B, because this algorithm B solved it. Or no, it's not an instance of that language, again, because this problem solved it. Then all we're going to do as our output is repeat it. Right? Now cover this up and treat it like a black box. This looks like an algorithm for A. Right? How does it work? We don't know. We don't care. Just like functions. One of the first things I ask in CS1 is, how does square root work? And what's the answer that I'm always looking for? Yeah, what was it? Who cares? Right? It just works. We're just consumers of the function. We don't have to actually build it. Right? It's a black box that you feed in input and you get this output. It solves this problem over here. Right? Now, inside the inner workings of this thing, it's applying this function that's mapping yes instances to yes instances and no instances to no instances. And it's using this as a subroutine. Right? So by building this black box here, you're not solving the problem. You are actually by building this, you are establishing this. Right? You're establishing this reduction. That if you can come up with this function that maps instances of A to instances of B, then A is no harder than B. B is at least as hard as A. Okay? Now, this gives us a notion of completeness. Right? NPC equals NP-Complete. And I'll forego the formal definition here, but this is all, and that's a hyphen, by the way. This is all problems such that, and again, I don't like what, usually we use P for problems, but we've already got that for a complexity class. And the way that that's solved, if you're actually typesetting this stuff, is that you use this formalized P, which is going to be a blackboard or like serif or something like that. And then you use this calligraphic one for problems, and this one for the class, the complexity class. But I can't do that here unless, I do this perfectly scripted type every single time. So all problems say A, such that A is in NP, and every problem, I got myself into a corner here because now we're going to go in reverse. So let me go ahead and reestablish this as B. Every problem A in NP reduces to B. In other words, again, A is no harder than B. Right? Every problem in the entire complexity class NP reduces to this one problem. Right? In other words, it's the one ring to rule them all, right? If you can solve anything in this entire complexity class simply by reducing it to this one problem, this one complete problem, solving that problem, and then you've solved all of the problems in the entire complexity class. Okay? Visually, what that looks like is the following. Here's our landscape. Here's NP. These are all the problems in NP. We've already established this, that these are all the problems in P. Right? NP-complete are the hardest of the hard. Right? NPC. Right? This is the hardest of the hard problems. They're the most complex of the complex. They're the most difficult of all the difficult ones. Right? If you've got an NP-complete problem, then everything in NP will reduce to it. And by the way, other NP-complete problems also reduce to every other NP-complete problem. So that establishes that this is going to be one class up here. Everything will reduce to everything else up here. Everything down here will reduce to something up here, and then consequently through transitivity will reduce to everything up here. But the real question is, can I take something that's NP-complete and can I reduce it back to something that's P? And if you did that, if yes, then P is equal to NP. And this entire landscape collapses down to P. Right? If not, if you can establish that this is impossible, then you've established that P is not equal to NP. Okay? That's the idea. That's by definition. Now, we need a starting point. The problem is, we need, our goal is to establish that certain problems, certain difficult looking problems, are NP-complete, right? In other words, they actually are difficult, right? Because nobody knows how to solve them in polynomial time, because nobody knows how to collapse this landscape, right? So they actually are pretty difficult, right? To establish, to do this, though, you need a starting point. Right? I have not given you an NP-complete problem yet. We've seen plenty of problems down here, searching, sorting, solving a system of linear equations. We've seen things that may look like they belong up here, Hamiltonian path, satisfiability, but we haven't established that yet. Right? You need a starting point. You need the first NP-complete problem. Okay? Now, what we can do is we can cheat, and we can define the following problem. Let L be, where is it? All encodings of machines and an input such that M is a non-deterministic Turing machine that accepts X in polynomial time. Well, non-deterministic polynomial time, right? So this is what's called canonically complete. All right? So I'll ask you another vocab word. What does canonical mean? Well, not cone like the other canonical, like canon. What is canon? Oh, no Catholics in the room apparently. What's canon in Catholicism? All right. What is canon in Star Wars? I'll ask it that way instead. When Disney bought Star Wars, what happened? No Star Wars fans apparently either, huh? When Disney bought Star Wars several years ago for billions of dollars, they took all of the extended universe stuff that had been built over the last 20, 30 years, like all the games, all the books, all the comic books, all the extra media, and they threw it out and said, we're going to start over. The only canonical Star Wars stories are the original trilogy, the prequel trilogy, and like Clone Wars or something, because they had, all that stuff, right? So they threw everything out and said that's no longer canon, right? Canon as in part of the regular story, right? Canon in this case means official, right? According to the definition. This is the canonically complete language, because it's by definition, this is complete. You can take any Turing machine that is a non-deterministic Turing machine that operates in polynomial time, and any input, and you can reduce it to this one problem. This is complete, right? By definition. Right? So what do they call it instead? Instead of canon, what do they call it in Star Wars now? Legends, that's it, right? All that extra stuff, the extended universe is all legends now, right? As part of an alternate reality or something, right? So all the good stories got thrown out, and instead we got the movies that we've gotten so far. All right. No Star Wars fans, apparently. Okay, fine. I'm not much of a fan anymore anyway. All right, Solo was really terrible. All right, so that was the first NP-complete problem. So a guy named Cook came along, and the person also named Levin came along and established the second NP-complete problem. And their theorem stated that satisfiability is NP-complete. And what they did, well, what Cook did at least, is he took the original language here, I'll call it L sub NP. He took this language, L sub NP, and he showed that you can actually encode any Turing machine, any non-deterministic Turing machine, as this huge circuit, which is not that surprising, right? He reduced it to SAT. Why is it not that surprising? Take any algorithm, implement it in Python. Ultimately, what is it? It's a program that runs on an operating system. That operating system runs on hardware. That hardware is a circuit, right? And so you can do something like this, where you can take any program, including non-deterministic programs, and you can simulate them using this large circuit. Right? So I'm not going to go through that because it's kind of tedious, right? It'd be like the equivalent of, again, writing down a Turing machine and then writing out a circuit for it, right? And if you've taken 230 or 231, you know how difficult or how tedious it is writing out circuits. We're not going to do that. Instead, we're going to establish other NP-complete problems. What we're going to do is we're going to show that we're not going to actually show this. We're going to do this another way here. 3CNF. Oops, CNF. There we go. All right. And we're going to show another problem here, reduces to Clique. All right. So this is the one that we're going to show with the remaining time here, and then probably extend it into tomorrow. All right. I'll introduce it, and then we'll have plenty of time to do the rest tomorrow. This was established by Cook and Levin. Right? This can be established very easily, and I'll explain what this is here in a second, just by taking a SAT formula and separating it out into what's called a 3CNF. A 3CNF is a conjunctive normal form, Boolean predicate, such that each, what's called a clause, has exactly 3 variables. And all we mean by this is you can take any formula that you can write down using a bunch of negations, ands, ors, parentheses, etc. And you can rewrite it in the following form. You can rewrite it as a conjunction, conjunctive normal form, of clauses, CI. These are clauses. Where you've got clause 1 and clause 2 and clause 3 ... and clause M. There are going to be M clauses. N variables, still, x1 through xn. And each clause has 3 variables. And it's disjunction. It has a disjunction of 3 variables. Right? It's not too hard that you can simplify any Boolean formula down to things where there are exactly 3 variables. So, for example, let's go with not this one. This one. x1 or x2 or negation of x4. And this is clause 1, right? It's a disjunction of 3 variables or its negation. Right? And here's clause 2. Negation of x1 or x3 or negation of x5. Right? And x2 or negation of x3 or x4 or something. And so this could be another clause, and this could be another clause. And say that there are 5 variables here, and there are 3 clauses in this one example. This is conjunctive normal form, 3CNF. This is just a clause, and all of the variables are ORed, right? They're all disjunctions. Each clause, you can take them all and take a conjunction of all of them, okay? So, this idea that you can take any formula and reduce it down to an equivalent 3CNF, we'll just take that as, yeah, you can do that. All right? That's not the point that I want to do. What I want to do is this reduction right here. And by the way, it is transitive, so that if A reduces to B, B reduces to C, A will reduce to C, and all the way over. So this establishes that the Clique problem, or Clique problem, which how do we pronounce that? Clique? Clique. Clique? Okay, that's how I would pronounce it too. I've heard other people pronounce it clique, but I pronounce it clique as well. This problem is the one that we were going to want to establish, okay? So we're not going to be able to go through the entire process today, but I do want to understand what that is. I think I've given it to you before, but if not, that's fine. Here's the Clique problem. Given a graph, G equals V comma E, and an integer K, does there exist a subset of vertices, I'll call it C sub V, right? Such that C is a clique of size. The size of that subset is going to be K. Right? So what is a clique? A clique just means that every vertex pair in C is connected. Okay? Here's a graph. Give me some cliques in here, or cliques. Does there exist a clique of size 3? Is there a subset of these vertices such that of size 3 such that they're all connected? Yeah, where? Those 3. That's a clique. Is there a clique of size 4? Where? this box, this one's connected to all three, this one's connected to all three, this one's connected to all three, et cetera, et cetera, et cetera. Right? So there is a clique of size 4, there's a clique of size 3. Is there a clique of size 5? What would that look like, by the way? Oh, I like to draw it as a home plate. Everything is connected. So what does that look like in isolation? It's a K, 4. What is this? K, 5. Right? What it's asking is there a complete graph, a complete subgraph within K of size K, or within G of size K? And that's what this question is. So, and maybe I'll ask it next year, because I think I have done it before as a programming assignment on your first homework to actually program this. Brute force. What's a brute force solution for this? What combinatorial objects are you going to be generating? Subsets. Right? For all subsets of size K. Right? In other words, n choose K of them. And you can look at this as, oh, hey, that's polynomial. Is it? What if K is n divided by 2? Then this becomes n to the n divided by 2. Is that polynomial? Definitely not. Right? So brute force will not work, but that seems like maybe that's the only solution. Right? So can we establish, in fact, nobody knows how to do this in polynomial time, because we can show a reduction from an NP-complete problem to this problem. Therefore, this problem is also NP-complete, because every problem in the complexity class P reduces to this problem, and transitively, therefore, every problem in NP reduces to this problem. So if you could solve the Clique problem, you could solve every single problem in this entire landscape that we showed before. If you just solve one of these problems over here, say Clique, in polynomial time, you collapse this entire hierarchy, this entire landscape. Okay? So how are we going to do it? Well, we're going to do it in I like to give you 5 steps. Right? And this is, I'll give you the 5 steps, and then that's where we'll end today. And I'll let you think about those 5 steps if you want to. Otherwise, I'll show it tomorrow. Let's see. Where's my 5-step process? Okay. Oh well, I lost it. 1, 2, 3, 4, 5. It should, okay. I don't know where it is, but I'll go ahead and remember it off the top of my head then. Here's showing a problem B is NP-complete. I don't like this. Let's go back over here. 1, choose a known NP-complete problem A to reduce from. Okay? And usually, and this step for our example is already done for us, because we're going to reduce from 3CNF to the Clique problem. Sorry, this is, I'll switch these around. This is 2. 1, show that B is in NP. Right? That's one. Remember, for something to be NP-complete, we have to show 2 things: that it's in NP and that every problem in NP reduces to it. So we do have to show this is in NP. Simply just design a guess and check algorithm for it. That's easy. And show that it's in the guess phase, of course, makes it non-deterministic. And just show that the rest of it, the verification phase, is can be done in polynomial time. Right? Then you define a mapping from problem inputs in A to inputs in B, right? So we're going to, in other words, we're going to take a 3CNF formula, and we're going to take that and output a graph G, right? And this is a very common technique with all these things. It's called a graph gadget. And all it is going to be encoding the information in this formula as a graph, as a bunch of vertices and edges, right? Then 4, we're going to show that this mapping called F is poly-time computable, right? And 5, we're going to prove that F preserves solutions. In other words, you're going to have to show a proof that yes instances map to yes instances, and by exclusion, no instances map to no instances. So you can show, yes maps to yes and no maps to no, or you can just show that yes if and only if yes, and then you can skip this one because it's by exclusion, right? Right? We remember that from, say, 235. P if and only if Q is equivalent to not P if and only if not Q. So if I establish an if and only if condition here from yes to yes, then we don't have to establish this one because it's already equivalent. So we'll show one way, and then we'll show another way, right? This is 2 proofs. All right. Any questions? Otherwise, we'll complete that tomorrow and show a few more other reductions.